So first speaker of the afternoon is Ruben Pellicer. He's going to talk about quantum diamond sensors. So whenever you want.
Thank you. Thank you, everyone, for making it to this afternoon Friday session. In these 20 minutes, I want you to have an overview of the different instruments that we have built in our lab. It's the Quantum Nanophotonics Lab in San Sebastián, Donostia, at the Material Physics Center. That it is at the university campus as well, in Donostia. And in particular, because I'm the first one of the people that are going to talk this afternoon about MB centers, I would like you to get a bit of an rough understanding of what's the principles, given that most of you likes physics, I guess. So MB centers, probably you have heard of them many times. They are of great interest in many labs. And you may be wondering, this has been already there for a while. I think in 2000, it started to pick up again, but it was already discovered in the 50s. And the thing is that it has been there for a while. There are a lot of tools, a lot of methods that have been proven in the lab. And actually, they are already being used, a few of them, in some scientific environments. But these are kind of loose pieces of knowledge until we put them back together. And that's a bit the effort that is partially what we are doing in our lab. And I know in the Basque community, there are different searchers. Like here, for example, Jorge Casanova is doing a great job on the theories to help us making from the theory these methods be useful, easier and practical to implement. Also, Technalia is doing their lab. And also here there is going to be a new laboratory at the university that they are going to help reinforce all these horsepowers to work together to make these concepts, these scientific, let's say, knowledge and advancements have what I call a real impact, but a reality is depending what you define, but I think hopefully it gets back to society in the sense of medical devices or technologies that improve our lifestyle. So I can say that we have done a lot of work here, but we have to work a bit on experience. And to do that, what we have done is to go in the lab, and we are leveling a little bit the experimental work. Quite a lot of weight goes in there, but also we do some work in the theories, because often, as you see, a wheel is not only composed of spokes, but also of the ring. So if we find that the ring is non-existent, that's our task to try to identify it and work together in the lab to find it or to collaborate with other colleagues. Going a little bit for you, giving you a bit of an overview of how this system works is a quantum state composed of electron spins. It starts with that, the story. So you have a carbon that it is, in theory, is just carbon in the diamond, no? And you have it's kind of an inert, let's say a cryogenic, but it's not cryogenic system that allows these electron spins to have long coherence times, even at room temperature. What creates these electron spins is actually that the carbon in some places is not carbon. It's a nitrogen and there is a vacancy next to it. And in one case is when there's an extra electron, you have the negatively charged MB center. And that's the one that is our playground, because it has two electrons that we can interpret it visually, like if we will have two vectors that they can be spin up, spin down, both of them, or one up and one down. So we have a triplet. And generally, the way we look at this in the real world, most of the times what we do is we have often, when we talk about a quantum state, it's spin up, spin down, two states, right? In this case, generally we pick either the +1 and the 0 or the 0 and the -1. But there is also some more advanced techniques that you can use both of them, double quantum. The beauty of this system, that it is nothing special, like nuclear magnetic resonance that is already being used in the hospitals, is that unlike the nuclear magnetic resonance, we can initialize it. What does this mean? That we can define this quantum state at the beginning, and that gives a lot of advantage. In this case, what we do, we shine green light, laser light, and the beauty of this system is if it's in the +1 state, it goes to the 0. And if it's in the -1 state, it goes to the 0. And if it's in the 0, it stays in the 0. That's the initialization, just with green light. Later I will show you that it's not even picky with the frequencies of the green light. It can be green-bluish light, and it still does the job. And there is a second side of it, that it also gives us the information. If it was in the +1, it shines, let's say, for a better understanding, it doesn't shine. In reality, it gives a bit of red light. The good is that on one side we shine with green, and we read with red. They are quite different, so we can differentiate easily the lights. And if it's in the 0, you have a lot of red light. So there you go. You can initialize. We will see later, we can play with the spin state, and then we can measure it. It's a destructive measurement, so whenever we shine green light to read it, we will destroy it. We will go back to the 0, and we will initialize it at the same time. This is a bit more, perhaps you like it more if you are missing this energy levels diagram. So here what we have is what I have been explaining, but a bit more, let's say, rigorous for physicists. So we have the ground state, and when we shine the green light, it goes to the excited state, triplet in both states, and it maintains the spin state. But when it comes down, that's where it comes the game. If it's in the, let's say, these two higher levels, they are the -1 and the 1. This is the 0. And up there is the same. So if it's in the -1 and the 1, it can take this path that is the one that allows that there is no red light coming out. And for the purpose of implementation, one can imagine that having a powerful green laser, very precise, it is expensive. It's not going to work if you want to make cheap devices. The beauty is that the absorption spectrum of these devices is very broad. So it can take, an LED can do the job. And the information comes also along a broad spectrum. And this spectrum, here you can see, is the Cerophone online that we have seen this morning, that some devices, they can have it very narrow. The MBs could have it quite narrow, but this is at room temperature, and the system works at room temperature. So it's a huge advantage. The Cerophone online is not that useful at room temperature. But here you can see, at the moment we use a laser. And here, before I forget, there is something that is happening with the magnetic field. When we introduce an external magnetic field, we have a Zeeman splitting effect. So the +1 goes up, and the -1 goes down, or the other way around, depending on the direction. And then here you can see that I have illustrated, okay, this is the qubit, but it can be the electron spin state that we can transmit it from one side to the other if there is an external magnetic field, because otherwise they are degenerated. We affect both at the same time, +1 and -1, we cannot tell. From there, we have like an equation that is showing us the possibilities of this device. In this equation, it's often shown in literature like it can do everything. At the moment, the reality is that you will see most of the works working with the magnetic fields and with the temperature. And we have done some experiments in the lab, and it has to do that the electric fields, you have to really put a high electric field for it to affect the measurement. So it is possible in this nanoscale, if the electric fields can be really high, then you can probably sense interesting stuff. But it's not that sensitive. And for the pressure, the strain is also related. It has to do when you put the pressure on the crystal, it tries to deform, and it brings some electronic field from the electrons. From this image, you can imagine that you can sense a lot of things. And this is not only the only tool that you have to sense things with the MBs. You can also use the coherence times. What happens is that the MB has some T1 and T2s we have seen today, T1s and T2s and T2 stars. But in the presence of, for example, other electrons, like could be free radicals, if we are looking at the medical applications, the free electrons, they can interact with the MBs and make them decohere. And when they do this decoherence, often the free electrons are related, for example, with pH in the blood. And it is a symptom of something perhaps going wrong in a cell. then you can sense, you have an extra tool to sense with MB centers. And here it's just an illustration of the complexity and the different prototypes and all this range of different attempts to sense things with MBs is because depending which application you are after, you want one configuration, you want one hardware. If you want to sense magnetic fields of the room or of the Earth, you may want a lot of MBs because each MB is going to send you information and then you average up very quickly. But if you want, when you have a lot of MBs next to each other, they have shorter coherence times because they affect each other. And in this case, if you want to sense very nicely the spectral differences in the magnetic field that you want to sense, for example, you may prefer to have single MBs or MBs farther apart. And with this, I have already introduced you that there is a lot of applications that could potentially benefit of MBs. Potentially, that's where we are at. And that's why there is still a big effort to be done because this is not there yet. And it's already proven in the labs. That's why here you can see material science and biology and physics. It's a tool that has already been pretty useful for many years. But if we want to give the step outside of the lab, that is where we have to put our forces together. And with this, I want to show you how it looks in the lab. Given that I have said that in the lab it's already useful, we built our first prototype thinking on a lab prototype. And basically what you see here, that it is an outdated figure, it's a whole set of optical lenses, mirrors, to be able to basically achieve the ideal case. That basically we have a green laser that hits the diamond. In this case, it's with a microscope objective, so we can have very high spatial resolution and look at single MBs individually. And then the MB is shining red light, and we have a dichroic mirror, so the green light is not going to the avalanche photodiode because the ratio in between green light and red light is pretty large. You have to shine, let's say, 100,000 times more green light to get 10,000 photons for one red photon, let's say, more or less. So we need to differentiate it. But basically it's microwave fields, laser, detector, and data acquisition card. In these sequences, they are is beneficial when you have a spin state to play with pulses. Some sequences, they are continuous wave, what we call, so we are constantly using one frequency or sweeping slowly, but when we use pulse sequences, we can have more diversity to be able to select what we want to measure. In this prototype, you may see at the top, this is one case that we were looking at a microfluidic chip that we made with Microliquids, a company from Mondragon, in which through this project we identified which materials are compatible with the experimental needs for this measurement, because many of the materials, they also shine red light and is not information. And from this device, we were also able to look at single diamonds. In the case of the single diamonds, we bought a diamond powder, and in this diamond powder, we have, let's say, 40 nanometers diameter nanodiamonds, and in average, they have 1 MB. So what Jason is doing, you can ask him for more details at the poster number 15. He first looks, so this instrument has a nano positioner, it has very high spatial resolution, and Jason has made it sweep, and is looking point by point to find MB centers. When he finds them, he analyzes if it's really one single MB, and that's with the G2 measurement. Once he has it, he's looking into the relaxation times, for example, because we are collaborating with Technun, with Josu, that has given the talk about error correction, and Josu was telling us that it's very important for the qubits to know if the coherence time stays steady over time. It's something that it helps them define the error correction algorithm. Probably this is completely incorrect. I don't see Josu in the room, so, oh yes, oh, is it correct? more or less. So choosing, knowing this information, because the T1 and T2, we always speak that it is constant. And apparently it is not. And for the people that design these algorithms is very meaningful. So this is some experiments that we got with some pulse sequences. Here you can see that we need to pulse the sequence. So it has to be, in time-wise, it has to be controlled with an FPGA, with something that it is real-time instrument. And from the nanodiamonds, it's one possibility to look at the micro world, but you can also look at the micro world with a bulk diamond. In this case, we wanted to know, we designed a microwave antenna, and we wanted to know inside the microwave antenna what is the field that we are actually generating, the field strength, and the direction. And thanks to putting one bulk nanodiamond, here you can see the dimensions. In this case, it's 1.5 by, so 3 millimeters by 3 millimeters width is pretty big. If you lose it in the lab, if you drop it, this is very handy. You can measure the magnetic fields, and we did this mapping, and it's very close to the simulations we did. And you can know in space with very high precision what is the magnetic field. In this case, is by looking at the Rabi. And not only that, but because this antenna also has 2 ports, and we can generate circularly polarized fields, which it comes out to be important. Before I said that the -1 and the 1, we cannot differentiate. But actually, that is not completely true, because with the polarization of the microwave, we can differentiate. We could tell it's a -1 or it's a 1. So in that case, we were also looking at the circularity of the microwave antenna. And with this, we thought, this instrument is cool, but it's very big, and we were already having some collaborators interested on doing extra things, like, for example, doing machine learning, because the signal is pretty noisy in that system, because it's looking at a very small volume of it's a confocal instrument, or it can be also amplified a bit the volume. So one of the things we did is, let's look at a bigger volume to get more MBs, and let's generate something that enables looking at a lot of different magnetic fields. And to be able to do that, we created an electromagnet, and the electromagnet, we can rapidly, with some electronics, create different magnetic fields, acquire the signal, and the idea is to do machine learning training that we are doing with Marcos and Estivali from Tecnalia. So with this system, we are able to rapidly generate a lot of data with very high quality, because if we look inside of the system, we have made some purpose-made hardware that collects a big part of the fluorescence. One of the problems of the MBs is that the fluorescence doesn't want to go where you want it to go, it goes anywhere. And it actually doesn't want to escape the diamond, because in the diffraction index difference of the diamond, 2.5, 2.4, and the air is very, very large. So with some design of ray tracing, we are able to get a very high SNR. With this in mind, you can imagine that we can start generating the data. And there it comes something that it is a complexity, and at the same time an advantage, because we can also know the direction of the magnetic field, not only the magnitude, but also the direction, which is it's not unique to this sensor, but in between the magnetic sensors world is pretty handy. And it's not that common. And this comes because if the nitrogen and vacancy axis, so we have a single crystal diamond, I didn't tell you, but you will always find 4 different orientations, possible orientations within that diamond. And it depends if the nitrogen vacancy axis is in one of these 4 configurations. The Zeeman splitting happens nicely, that it is in the case is perfectly aligned with the MB axis, the external magnetic field. Basically, you can think of it as a projection of the magnetic field onto the axis. That's pretty much the shift that you generate. And then you can see that there are some non-linearities, and it is because it's not only the projection, there is a little bit of the transversal components that also affect. So looking at this, we with Tecnalia, okay, we have it, we have the system, we can generate data, and we did generate it. And the problem, well, here you can see all the different vectors. We can make them larger, smaller, and we have these signals. And thanks to Julia, that you can see on the poster number 8, Julia is working on automatizing this process of creating the data and curating the data and labeling it. Because I don't know if you know that a very big part of the machine learning is to be able to create reliable labels, because that's what it teaches, actually. And that's, there is a lot of people being paid to label pictures that you use in Google Lens and all these things, for example, no? When the labor of Julia is trying to automatize it. And much to our sorry, we have to tell Technalia that we cannot tell them exactly the direction of the magnetic field. We can tell them the strength, but what happens is for each of this one, for example, this signature, that you have the 4 peaks, because, 8, is because we have a symmetry axis. Let's say this is the -1, this is the 1, doesn't need to be like that. So each of the axes, 1, 2, 3, 4, can be flipped, each of them. So we have 48 possible configurations, possible right answers for that footprint. And this is a little bit, this is a bit less intuitive, but all the 48 configurations that you can have. So if you look at it as a ball, you will have a football with a lot of different patches. How am I going on time? Okay, 5 minutes, thanks. So if you want to know more, Julia over there can answer you in the poster number 8. And this is, then we looked at this magnify, we call it, with these electromagnets, and then we realized sometimes we want really high magnetic fields and we want it to be very stable. And that was a problem because the electromagnet is current, it's not a superconductor, and it has noise, and it has limited magnetic field strength that we can generate with these magnets. And also, within that volume, we want to introduce microfluidic systems, we want to introduce perhaps bigger coils or microwave antennas, so we have to make more space. And this was the third prototype that luckily in the lab, we are getting one for each at this moment to play, one of these toys to play. So basically, it's a set of permanent magnets in this case, because that's the most quiet source of magnetic field that can be achieved. And we have one ring that is the orange inside, one ring, it's kind of a pair of rings of the gray outside, and by rotating the inside with respect with the outside, we can change the magnetic field inside from 0.1 millitesla or less to more than 0.1 Tesla, and it stays very stable. Why 0.1 Tesla? I will show you later that it has some specific features that we want to explore later down the chain. And this is a picture of how it looks in the lab. And here you can see there is also a lens and a photodiode. This time, this second iteration, we could buy one that was closer and less magnetic, less ferromagnetic. So it will distort less the magnetic field. And which number of slides is this? Okay, I'm going to finish soon. 2 minutes, cool. So I was saying, why do we want to go to 0.1 Tesla? And there is a regime where the -1 gets close to the 0. And I was saying before that with microwaves, we can do this play in between spin states, 0 and 1. But it can also happen naturally. If we bring it to this sweet spot, and this is in the ground state, in the excited state, there is an equivalent 1, a little bit at a different frequency, a different field, sorry. It happens naturally. And when is this useful? When we want to, what we call, transfer the magnetization, hyperpolarize to the nuclei. So we are getting into the playground of the nuclear magnetic resonance, where we cannot initialize, and we are hoping that through these mechanisms we can get a lot of initialization in the nuclei as well. So we can get much better signal-to-noise ratio. And this is an example of the work of Asier with this device. He has acquired the signature, and he's playing with trying to detect different strategies to look at the nuclei. He's starting to play with it and looking at the system response. So this is this is the fingerprint. You see again the peaks, 4 on this side, 4 on this side, and on each peak you may see 3 little dints. And this is the hyperfine interaction. So the electrons is already looking at the nuclei of the nitrogen that is next door. In this case, it's a triplet. That nuclei. The nitrogen could be 14, that is a triplet, or 15, that it is a spin-half system. And he has already, I'll leave it to Asier. If you are interested, go to his poster. And the number for, well, it's not numbered out there, but Asier is there at the back. I should have put a picture so they recognize you. And here, Asier will show you that if we are in this peak, for example, he's pointing at this one. So if we try to look at the frequency of this one, how it couples to the other two, how this guy looks, sees the frequency of the colleagues around, because he's in the center and it's symmetric, he will see only one peak. Is both frequencies fall on the same peak. But if it's on one side, the system will see two frequencies. And with this, I'm finishing the talk. There are other possibilities like qubits. And one of the examples that we are working on is that we did some qubit classifier, single qubit classifier with a photonic system. It was in the polarization of the light, the trick. And it will be interesting to extrapolate it or bring it to the MB centers because the learning in the photonic system had to do with rotations of the Q plates and it's very slow. And in this case, it's programmatically, the sequences are rearranged very quickly. And with this, I would like to inform you that there are other topics in the same lab happening. If you have interest, you are always looking for people to see the lab and people that want to join forces. Thank you very much.
Okay. Why not? You have a question? No? Okay, no. You have one or not? Okay. So I have a question about the practicality of when you do the measurement, you said that you are destroying the qubit, right? But then you need to do several measurements because you are not detecting 100% of the photons. So what does it imply? I mean, if you are destroying the qubit, how do you keep the information? Maybe, yeah.
Yeah, you have to repeat the measurement many times. In the case of the error of the NBs, is really huge for a qubit. So we are using, for example, 1 million times acquisitions to be able to average out more than 1 million times. Yeah. And one trick, depending what's the interest of that qubit, can be to have many MBs at the same time, and they will. It's kind of a classical view of the qubit. You initialize them all, you manipulate them all, and depending the application, that could be a workaround to reduce the times.
Okay, thanks. So if there are no more questions, let's thank Ruben again.